Okay, let me first take roll. And today is the 5th. Pay attention to those guys who are online. Anderson, Chesmore is here. Gonzalez, Iki, Islop, Jabbar, Jones is here. Labrador, McKeon.
Here.
Miller is here. Peterson.
Here.
Papa, Simpson, and Welter.
Here.
All right. You guys out there in Zoom, can you hear me?
Yes.
Oh, I can't hear you. Hold on.
I can see you turn down your speaker.
Oh, okay, maybe that's the reason why. So let me, okay, Miss Miller, can you hear me now?
Yes.
Oh, it's still kind of low. Well, I know she's kind of soft-spoken, so that's probably the why. Okay, so let's, now, remind me, where did I stop the last time? I seem to recall we did up to here. Did we do this example? Or where did we stop? Let me just give me an idea.
Last thing in my notes is the partial pressure equilibrium constant.
This.
Yeah.
Okay. So I did not get, okay, so just to recap, so that we can go into the next example. It says, we're talking about here gaseous systems, right? Where all the components in the mixture at equilibrium are gases. So basically, we can write down what is called Kp, which is the equilibrium constant in terms of partial pressures. Very similar to Kc, the only difference is that we use concentration terms in the equation instead, I'm sorry, we use pressure terms in the equation for calculating Kp instead of concentration terms. So basically for the hypothetical reaction that we saw earlier, let me go back to full screen here. Let me get all this here. Oh, good, I can take that across there, okay. Right, so for the hypothetical reaction that we saw earlier, and just to remind you of what that equation is, that equation is, oops. Okay, not writing, what's going on? Okay, so the equation is AA plus BB to form G, uppercase G, plus H, uppercase H, right? So that's a system, that's a hypothetical system, and we're assuming that these are all gases, right? So we have the back and forth, and therefore Kp is equal to the pressure of G raised to the G times the pressure of H raised to the H divided by the pressure of A raised to the power of A times the pressure of B raised to the power of B. So that's basically how you calculate Kp. And just as in the case, I don't know if I made this point the last time. If you remember, I said that when you're calculating Kc, we're not concerned about the units of Kc. The same is true for Kp, all right? In fact, the same will be true for every K that we're going to meet later on, all right? Which reminds me, I noticed when I was grading the assignments dealing with kinetics, that some of you, a good number of you, used uppercase K for the rate constant, right? I didn't take off any points for this, but just to let you know, you should use lowercase k for the rate constant, not uppercase K, because you don't want to confuse the rate constant with the equilibrium constant. All right? So just for future reference, all right? I did not penalize anybody in grading that assignment when I noticed that, but that is actually incorrect. All right, so back to this now. So I also talked about the fact that the relationship between Kc and Kp is given by this equation. I think I derived it already for you guys, so I won't go through the derivation again. But basically, Kp is equal to Kc times RT raised to the delta N of the gas, where delta N is a difference between the sum of the coefficients of the products minus the sum of the coefficients of the reactor. All right, so that's a relationship between Kp and Kc. Okay, so that's just a bit of review from last time. So based on that, we should be able to do this problem right here. It says consider the equilibrium between dinitrogen tetroxide and nitrogen dioxide, and it gives the equation and it gives you the Kp value. So the question is, what is the value of Kc for this reaction? So just to remind you what we saw earlier, Kp is equal to Kc, times RT raised to the delta N, right? What the question is asking for is Kc. So we can rearrange this equation to get Kc is equal to Kp divided by RT raised to the delta N. And then all we have to do is plug the number in, or the numbers in, 0.660 for Kp divided by R, which is 0.0821 times the temperature. What's the temperature? 319 Kelvin. And all of this must be raised to delta T. I'm sorry, delta N. So what is delta N again? Delta N is the sum, is the difference between the sum of the coefficient of the products minus the sum of the coefficient of the reactants. So in the case of this reaction, the sum of the coefficients of the products is 2. The sum of the coefficients of the reactant is 1. So therefore, delta N, let me just erase this here and replace it with the actual difference. So I'm just going to erase this here. Okay, so this part here is going to be 2 minus 1. And that's it. Of course, 2 minus 1 is going to be equal to 1. So let me get my calculator to work this out. So it's going to be 0.660 divided by 0.0821 times 319. So according to my calculations, this is going to be equal to 0.0252. And that's how we determine Kc. All right? Any questions about the A part that we just did? Any questions? No questions? All right. Okay. So the next question says, what is the value of Kp for the reaction? And it gives you this equation right here. All right. So this here that we just did is the A part. So for the B part, they gave you this equation here, right? Now, when you compare this equation to the equation that was given here, what do you notice? When you compare this equation, right, to this equation that was given here, what do you notice? It's flipped, right? The products become the reactants and vice versa, right? So what does that mean for the Kp value of this reaction right here? I'm going to call it Kp prime. What would that be equal to? If you flip the reactants and products, what happens to the Kp value? Exactly. So you're going to get 1 over the original KP value. So that'll be 1 over 0.660, whatever that gives. Okay, so according to my calculation, this works out to be 1.52. All right. Okay, any questions about this particular one? Any questions? All right, in the C part, it says, if the equilibrium partial pressure of NO2 is 0.332 atmospheres, what is the equilibrium partial pressure of N2O4? So, first thing I would write down is the expression for Kp based on those two components, based on this equation actually, and Kp would be equal to the pressure of NO2 squared divided by the pressure of N2O4, right? What the question is asking for is the pressure of N2O4. So we can rewrite this as pressure of N2O4 will be equal to the pressure of NO2 squared divided by Kp. And then all we have to do is plug the numbers in. They gave you the pressure of NO2 as being equal to 0.332. So I'm going to put 0.332 squared divided by the Kp, which is 0.660. So 0.332 squared divided by 0.660. And according to my calculation, this works out to be equal to 0.167. And the units would be atmospheres. And that's how that is done. Okay, any questions about this particular example? Any questions? Any questions? Okay, so let me move on to the next slide. So now we're going to look at situations where you have an equilibrium system where pure solids and liquids are involved. And what you'll notice is that we have to kind of treat this a bit differently from what we have been looking at before. The first thing I want to say is that when it comes to pure solids and liquids involved in a reaction, even though the amounts of these substances might change as the reaction proceeds, what you need to understand is that the concentrations do not change. Now, this might sound weird, but let me explain why that is so, and I can do so mathematically. So firstly, let me just remind you that the concentration of anything, how should I put this? Okay, let me just do it here. I'm going to remove it eventually. So the concentration of anything would be the moles of that thing divided by the volume in liters, right? Now, the thing about moles is that moles can be expressed as mass in grams. I'm going to use lowercase m for that. Divided by the molar mass, I'm going to use uppercase M for that, divided by V, all right? Now, M over V is going to be equal to the density. So we can rewrite this as density over molar mass. And the thing about this expression for solids and liquids, this expression is a constant, right? And that's because for solids and liquids, density is considered to be a constant, even though it does change, but ever so slightly. And M, the molar mass, is also constant. So basically, you have two constants, one divided by the other, that will give you a constant value. So basically, for solids and liquids, the concentration does not change. And that influences how we write down the equilibrium expression involving solids and liquids occurring in a reaction, all right? Okay, I need to erase this, so, okay. All right, so let me erase this here and continue. So this is the point I just made. Even though the amounts of the solids and liquids will change in a reaction, but the concentrations do not change. So just to give an example, so we have this reaction where calcium carbonate decomposes to form calcium oxide and carbon dioxide, right? So we have a solid reacting to form a solid and a gas. So therefore, what you'll find is that the proper way of writing the Kc is not what you see here, which you probably would have done based on what we have talked about before. Basically, what we do is ignore the solid involved in the reaction and write down the Kc in terms of the only substance which is not a solid or a liquid, it's a gas, and that's carbon dioxide. So in this particular case, we just write down that Kc is equal to the concentration of CO2, and that's it. All right? And if you had liquids involved, you do the same thing. You would simply just ignore the liquids for the same reason why you would ignore the solids. All right? Okay, so to give an example, let's look at this question here. It says, it gives you the equation, and it says, write the equilibrium constant expression for this reaction, right? So it's, again, product over reactant, but you'll notice that we have a solid here. So in this particular case, Kc is going to be equal to the concentration of carbon monoxide times the concentration of hydrogen divided by the concentration of water vapor. And that's it. We do not include the carbon in this equation. And that's basically how you'd write down the Kc in those kinds of situations. All right? Okay, any questions about this? Any questions? Yes, sir. Always ignore the solid and liquid if there are any liquids involved when you're writing down the Kc value. Okay, so let's talk about the equilibrium constants, how we interpret them, what do they tell us about a particular system at equilibrium. So the first thing I'm going to say here is that if the Kc or Kp or any of the Ks is large, because we're going to meet some other constants later on, equilibrium constants later on. If it's large, what that tells you is that the ratio of the reactants, the ratio of the products to reactants is high, which means that you have a relatively high concentration of products compared to the concentration of the reactants. So basically, if it's extremely large, you can pretty much assume that the reaction has gone to completion, which means that the amount of reactant that is present is very, very small. On the other hand, the opposite is true. In other words, if Kc or Kp is small, then basically the reaction favors the reactants, and therefore the amount of products that will be present at equilibrium will be very, very small. All right, and that's going to be very important when it comes to predicting the direction that a reaction would go to achieve equilibrium. Another thing I want to say here is that the equilibrium constant expression applies only to a system at equilibrium, right? So if a system is not at equilibrium, then we cannot write down Kc is equal to concentration of products over reactants. We have to use a different term, which we're going to meet later on. And here's a very important aspect of chemistry that is considered to be very important, especially for those of you who have to do organic chemistry. You'll be looking at a particular reaction in more detail where this particular aspect comes into play. It says here, although a reaction may be thermodynamically favored, it may be kinetically controlled. Now, what does that mean? It means that basically there are two aspects of any chemical reaction. You have the thermodynamic aspect and the kinetic aspect. The kinetic aspect we talked about earlier, that basically has to do with how fast the reaction proceeds. The thermodynamic aspects basically determines or predicts whether or not the reaction will take place, right? One key thing that you have to understand is that the fact that a reaction might be thermodynamically favored does not necessarily mean that the reaction will proceed at a fast rate, and vice versa, all right? So you can have a situation where the reaction, you know the reaction is going to take place, and we're going to talk about that in a later chapter, the thermodynamics chapter, where we're going to talk about whether or not we can predict a reaction will take place. But the fact that the reaction will take place does not necessarily mean that the reaction will proceed at a very fast rate. So basically, those are two aspects that, especially again in organic chemistry, that we have to take into account whenever we're looking at product formation. Okay, so let's look at this example right here. It says, based on what we have just seen in the last slide, gives you this reaction, and it asks if this reaction is likely to occur at any appreciable extent at 298, and it gives you the Kp value. Now, there's a bit of a typo right here. This here should be an exponent, so this should be 10 raised to the 22, all right? So please make a note of that, all right? So the question is, will this reaction occur to any appreciable extent? Now, to answer that, we have to write down the Kp expression, which in this case would be product over reactant, but these products are not are solids. So basically, in this case, Kp will be equal to 1 over the concentration of CO2. All right? So basically, if this is a high number, 5.3 times 10 to the 22, what that means is that the concentration of CO2 is very low. 1 over 5.3 times 10 to the 22, right? So as you can imagine, that would be a very low number. So the fact that the concentration of CO2 is very low means that the reaction will not occur to an appreciable extent. In other words, the equilibrium system will favor the carbon dioxide on the reactant side and not anything on the product side like the calcium carbonate. And that's basically how we answer that question. All right? Any questions about this? Any questions? So the answer is no. All right? Okay, continuing. So now we're going to introduce to you a situation where the system is not at equilibrium, right? So we have this thing called a reaction quotient, right? And represented by Q. Q is basically the same thing as Kc or Kp, excepting that it's not necessarily representing what happens at equilibrium, right? So it says here, for non-equilibrium conditions, the expression having the same form as Kc and Kp, that's called the reaction quotient, right? Which would be Qc if the concentration terms are used, or Qp if the pressure terms are used, right? So we specifically use Qc and Qp basically to represent the ratio of products to reactants at pretty much all times, including non-equilibrium conditions, all right? Now, this is important because we can use the fact that, one, the reaction quotient is not constant, but we can compare it to the Kc value to make predictions as to which direction the reaction will shift in order to establish equilibrium, right? So as we say here in this line right here, basically we compare the magnitude of Qc to Kc to make such predictions. And I'm just noticing somebody said something in the... Oh, okay. I just saw your thumbs up, Daniel, Ms. Jones, so thank you. Okay, so how do we make such predictions, right? So this diagram basically summarizes how we do that quite well, if you ask me. So basically, let's say we start off with a situation where we have only reactants and no product, right? That would mean that Q, and that could be Qc or Qp or Q whatever, Q would be equal to 0 because there are no products, you have reactants, so Q will be equal to 0. So in order for the system to achieve equilibrium, the reaction would have to go forward in order to produce more products, which means that the concentration of the reactants will decrease. So therefore, that's why we have this arrow here showing the direction of the reaction, right? So remember now, we're going from reactants to products, all right? So if we have no products to begin with, then basically the equilibrium or the reaction will shift to the product side to achieve equilibrium. In this case here, we do have some products, but the thing is that the concentration of the products is small, not large enough to get this ratio being equal to Kc. In other words, the concentration of the products divided by the concentration of the reactants would be less than Kc or Kp or K. What does that mean? That means that, again, in order to achieve equilibrium, the reaction would have to shift to the right, favoring the formation of products, increasing the concentration of products, decreasing the concentration of reactants, and therefore, when that happens, you're going to get to a point where the concentration of the products is such, and the concentration of the product of the reactants are such that Q becomes equal to K. At that point, the system will be at equilibrium, all right? And therefore, the net change will be no change because, of course, it's at equilibrium. The rate of the forward reaction will be equal to the rate of the reverse reaction, all right? Then we get to the other side here, where the amount of products here is high compared to the concentration of reactants, such that this ratio is greater than Kc. What does that mean? That means that in order for the system to achieve equilibrium, the concentration of the products would have to decrease, and the concentration of the reactants would increase. In other words, there's a net shift to the left, as shown here, and therefore the system will continue to do so until it achieves the equilibrium as mentioned here. And then finally, if there are no reactants and only products, again, the shift will be to the left. In other words, some reactants would have to form, the concentration of the products would decrease, and the QC value or QP value would decrease until it becomes equal to the K value, right? So that's very important, as you're going to see in some calculations that we're going to do in the examples that will follow this slide, all right? Okay, any questions about the reaction quotient? Any questions? Any questions? All right, so this is just summarizing what I just said right here. If Q is smaller than K, then the denominator of Q is too big. We have too much reactants, and therefore we're going to shift to form more to form more products. If Q is equal to K, equilibrium is achieved. But if Q is larger than K, then the reaction will shift, favoring the formation of reactants, decreasing the amount of products, and therefore will achieve equilibrium after that. All right, so let me move on to a very important principle known as Le Chatelier. I always used to call it Le Chatelier. I still do that from time to time. So please forgive me if you are a French-speaking person. Don't feel insulted, all right? This guy, he came up with a very important principle which makes predictions as to what would happen to an equilibrium system if you make certain changes, right? And the different factors that will affect equilibrium, I'm just going to list them here. The first one we're going to look at is concentration, right? Of the different items, the different components of the system in equilibrium. The other factor that would affect equilibrium is pressure changes, right? But this would apply to gaseous systems. So let me just put this here, right? Specifically, this would apply to gaseous systems in equilibrium. The third one is going to be temperature, right? We're going to see how temperature affects the system at equilibrium. And then the fourth and final one is the addition of a catalyst, all right? So these are the different factors that we're going to look at to see how they affect the system in equilibrium. But let me just talk about Le Chatelier's principle. If you look in different textbooks, you'll see it's worded differently. The way it's worded here is that when any change in concentration, temperature, pressure, and volume are imposed on a system at equilibrium, the system responds by attaining a new equilibrium condition that minimizes the impact of the imposed change, all right? So that's a bit wordy. Basically, what that means is that if you already have a system in a state of equilibrium, and you all of a sudden make a change to the system, right? Whatever the change that you're making to the system will respond by opposing the change that you imposed so as to reestablish equilibrium, all right? The key thing you need to remember is that when you make the change on the system will no longer be at equilibrium at that point, but the system will respond to try to attain equilibrium by doing the opposite of the change that you imposed on the system. I hope I'm making it clear, all right? So whatever you do to the system, you disturb the equilibrium of the system will respond by doing the opposite to reestablish equilibrium, all right? That's basically what Le Chatelier's principle is saying. So let's look at the situation where the system is at equilibrium, where Q is equal to Kc, all right? So basically what we're looking at here is a situation where you increase the concentration of one of the reactants, right? And then all of a sudden, the system is no longer at equilibrium. The result of that is that the denominator of the reaction quotient increases, right? The result of that would be that Q is now less than Kc. So if Q is now less than Kc, what will the system try to do? The system will try to make changes such that Q is equal to Kc again. So how does that happen? It happens by basically causing the equilibrium to shift, favoring the product side, right? It will shift to the product side, and therefore the concentration of the products will increase, and therefore the QC value will now get to the Kc value as a result. It will increase to get back to the Kc value, all right? And if you understand this, then you can understand what happens if the concentration of the reactant is decreased. So let's say you decrease the concentration of reactants. What that means now is that, let me just cross this out temporarily. So what that means now is that QC will be more than KC, right? And if QC is more than KC, that means that this condition is temporary, again, in order for the system to restore to equilibrium, there must be some changes, and the change that will occur is that in this case, the equilibrium, well, the products would now decrease as a result of that change, and the equilibrium now will shift to the left. All right? So that's basically how Le Chatelier's principle explains that whatever you do to the system will do the opposite in order to restore the equilibrium after you disturbing that system. So just to give an example of this, here is, I'm going to write down the equation for this reaction. The reaction is between acetic acid, which is of this formula, plus 1 octanol, which is a rather large chain of carbon atoms. I'm going to simplify it. We'll write down everything. Okay, so this is CH3, and then you're going to have 6 CH2 units, and then COOH. So this is acetic acid. Acetic acid. This is 1O. I'm sorry, too many oxygens here. 1 octanol, not. Come on. Okay, so this should be OH. In fact, this should be 7 here. Let me erase this here. Okay, so this should be OH, all right? And then you have the equilibrium between those reactants and the product here, which is octyl acetate, which has this formula CH3, CH2, 7, O, and then OCCH3 plus H2O. All right, so that's the reaction here. It's an organic reaction. All these compounds are organic except in the water. Okay, so that's the equilibrium that this graph is all about. So this graph is plotting concentration versus time. Okay, so initially you have a certain amount of acetic acid, a certain amount of 1 octanol. So before the system is not at equilibrium, the reaction takes place. What happens is that the concentration of both reactants fall, the concentration of both products rise until you get to a flatline situation. So basically, at this juncture right here, you're going to have equilibrium. All right? When all the concentrations of all the species are constant. Then all of a sudden, somebody decided to add acetic acid. So the concentration of the acetic acid jumps from here to here. What that means is that the system is no longer at equilibrium, right? Now, according to Le Chatelier's principle, if you make a change to the system will oppose the change that you made. So this person decided to increase the concentration of the acetic acid. So the system will decrease the concentration of acetic acid. But when it does that, the concentration of 1 octanol will decrease as well. And the concentration of octyl acetate and water will increase because they are the products. And then you have a new flatline situation. So this is a new equilibrium position. So I'm going to call this equilibrium state 1. This is equilibrium state 2. All right? So basically, that's what happens. That's how the system responds. Whatever change you make to the system will respond by doing the opposite in order to restore equilibrium. All right? Okay, any questions about this? Any questions? All right, so here is another example. And again, this is using the same reaction that we just looked at. It says water can be removed from the equilibrium mixture in the reaction of 1 octanol and acetic acid, for example, by using a drying agent that is insoluble in the reaction mixture. Describe how the removal of a small quantity of water affects equilibrium. Okay, so this is the same equation that we talked about before. And what this question is saying is that if you remove the water, right, then basically it will, hold on, what the question is, the water can be removed, for example. Oh, so basically what the question is asking is, if you remove the water, how does that affect the equilibrium of this system, right? So remember what we said in Le Chatelier's principle, what it says. Whatever you do to the system will try to do the opposite in order to restore equilibrium. So when you remove the water, you're disturbing equilibrium, right? So basically you're decreasing the concentration of the water. According to Le Chatelier's principle, the system will try to decrease the concentration of water. So therefore, what will happen is that you're going to have a shift to the product, right? So therefore, by decreasing, the way I would answer this question is that by decreasing the concentration of water, the system will respond by increasing the concentration of water, and this is achieved by the equilibrium position shifting to the right. All right? So that's how I would answer that question. You're decreasing the concentration of the water. The water is removed. You're decreasing it. The system will do the opposite. The system will increase the concentration of water to reestablish equilibrium, and therefore it will shift to the right in order to do that. All right? Okay, any questions about this? Any questions? Any questions? No questions? Okay, let me see something here. Okay, before I move on, let's look at this question in your assignment, question number 4. It says at 500 degrees Celsius, the equilibrium constant for this reaction, which is the Haber process, is 0.080. It says, given that the concentration of ammonia is that, concentration of nitrogen is that, concentration of hydrogen is that, find Q and predict how the reaction will proceed, right? So Q, let me turn on my writing thingy. Okay. Where is this? Oh, wrong place. Okay. Okay, so Q, more specifically QC, so let me write down here, QC is equal to, based on this equation, the concentration of ammonia squared divided by concentration of nitrogen times the concentration of hydrogen Q. Right? So we put the numbers in. The concentration of ammonia is 0.0596 divided by concentration of, oh, this should be squared. Can't forget that. Divided by the concentration of nitrogen, which is 0.600, times the concentration of hydrogen, which is 0.420. All right, so let's see what that gives. 0.0596 squared. Oh, and this should be cubed. All right. Divided by, oh Lord, let me see, 0.0596 squared divided by 0.6 times 0.420 cube. Okay, so according to my calculations, this works out to be equal to 0.420 0.0445. Okay, so we have found Q, but the next question is predict how the reaction will proceed. Now, in order for us to do that, we have to compare QC to KC, and which one is larger? Of these two, which one is larger? That should be easy. Which has a larger magnitude? Okay, so therefore we can say that KC is greater than QC. So the question is asking, predict how the reaction will achieve. In other words, what will happen in order for the system to achieve equilibrium? In other words, what would happen to the reactants and the well, let me rephrase that. What would happen to the concentration of the reactants and the products such that KC can now become equal to, such that QC will now be equal to KC? Think about this equation here. How can you get this value here for QC to increase such that it becomes equal to KC? Okay, so the numerator would increase and the denominator would decrease, right? So that means that the concentration of ammonia would increase, which would be the product, and the concentration of the reactants would decrease. In other words, the equilibrium shift would be in that direction from left to right, based on the equation that is given. All right? So therefore, what that means is that at this point, some nitrogen will have to react with some hydrogen to form more ammonia. And at that point, it will continue to do that until you get to a situation where QC is now equal to KC. So therefore, the answer is equilibrium will shift to the right. Well, let me just say, since QC is greater than KC, since QC is greater than KC, the equilibrium will shift to the right to favor more product and decrease the amount of reactant. All right? Any questions about this one? Any questions? Any questions? Okay. Can I clear this? Going once, going twice. All right. I think I have another question dealing with QC. Okay, now this one says the equilibrium constant for the following reaction is 5.10. So that's the equation. If the concentration of carbon monoxide is 0.15 and the concentration of so this is basically the same kind of question, right? So how would you proceed? If you understood what we did in number 4, you should be able to tell me the answer to this one. Let me do my pen thing again. It gives you the concentration of each of these substances, and it's asking for you to calculate Q. So how would you calculate Q or QC? Let's write down the equation first before we put the numbers in. What's the equation? Based on this equation here, what's the mathematical equation for QC? QC is equal to what? I'm sorry? Well, concentration of H2 times,
CO2.
right, divided by, okay, very good. All right. So we put the numbers in, right? So for hydrogen, that's 0.42 multiplied by, for carbon dioxide, it's 0.37 divided by, for carbon monoxide, it's 0.15 and multiplied by, for water, it is 0.25 m. All right. And then we work that out. 0.42 times 0.37 divided by 0.15 times 0.25. Okay, and this is what I get. And please correct me if I'm wrong, but I got 4.1. All right? Okay, so now that we have 4.1 as the calculated value for QC, what would be the next step? Remember, the aim of this exercise is to determine which direction the reaction will shift or the equilibrium will shift after determining the QC value. So what do we do next in order for us to make that prediction? Now that we have QC, what do we do next? I'm sorry?
We look at QC, which is greater than QC.
Okay, so basically, QC, KC is greater than QC. Very good. So what does that mean? What will happen? How will the system respond? If QC is less than KC, you have to bring up, in order for the system to achieve equilibrium, the value of QC would have to increase in order to be equal to KC. Right? So how will the QC increase? Here's the hint right here. How would you increase QC? Right, so the numerator terms would have to increase, which would necessarily mean that this would decrease, right? So therefore, in other words, the reaction will shift again to the right. So therefore, equilibrium will shift to the right since KC is greater than QC. All right? Any questions about this one? Any questions? Any questions? Okay. Can I clear this? Going once? Going twice? Okay, so there may be one more question. Okay. Oh, this one is a Le Chatelier's question. But there's one thing. Okay, we have to cover some other topics before we can do this question. So let me leave that for the time being. And let me go back to the PowerPoint. Okay, what's happening here? Okay, what am I doing wrong? How can I get back to PowerPoint? Oh, okay. All right, so let's talk about a situation where we have what we call a heterogeneous equilibrium. What this basically means is that you have different reactants in different states, or different reactants and products in different states. How does that come into play when it comes to predicting the direction of equilibrium in a system? So, okay, so we're looking at this reaction that we saw earlier. Let me just remind you of what the equation is. The equation is CaCO3 solid to form CaCO solid plus CO2 gas, right? So here we have a situation where two of the components, there are three components, two of the components are solids, and the third component is a gas. So let's say we start off with, in a closed system, we start off with a certain amount of calcium carbonate, right? And then what happens is that the reaction proceeds because these are the products of the reaction. So the equilibrium, the reaction will shift to the right in order to achieve equilibrium. And at equilibrium, you're going to have carbon dioxide filling up the container. But in a solid state, you're going to still have calcium carbonate, and that would be mixed with some calcium oxide. So this would be the state of affairs at equilibrium. Now, what happens if you add some calcium oxide to this system at equilibrium? Well, the answer is nothing will happen. The pressure of carbon dioxide will remain unchanged, And that's because calcium, even though you're adding more calcium oxide, you're not changing the concentration. Remember, solids and liquids, their concentrations do not change, right? If there's no change in concentration, then there's no change in terms of the equilibrium shift, all right? And the same is true if you add some calcium carbonate to the system, same thing will happen. There'll be no equilibrium shift, and therefore the pressure of the carbon dioxide remains the same. So basically, what we're learning here is that if you change the amount of solids or liquids in a system in equilibrium, nothing will happen, right? And that's because there's no concentration change. Okay. And that's all we're going to say about that for now. Now, what we're going to look at now is a second factor that affects the equilibrium position, and that is changing the pressure or volume. And what you're going to see is that changing the pressure is basically the same thing as changing the volume. The only difference is that there's an inverse relationship. So let me just get into this. So let's say that you have a system in equilibrium, and let's say that you change the pressure of one component of the equilibrium mixture, one gas, right? You don't change the pressure of the other gases. Well, one thing you need to remember about this is that, and this comes from the ideal gas equation. I'm going to squeeze it up here. Remember this equation? P is equal to N over V times RT. Well, the N over V here is the same thing as concentration. So we can put concentration of gas times RT. So what this is telling us is that the pressure is directly proportional to the concentration. So whatever arguments or whatever explanations you can use to explain the change in concentration and the effect it has on equilibrium, it's the same thing with pressure, right? In other words, the pressure can serve as a proxy for measuring the concentration of the gas, right? So as stated here, when you change the pressure of one component in the system at equilibrium, that leads to the change in concentration of that gas, and therefore the equilibrium position will shift in order to decrease the concentration of that gas. Again, whatever you do to the system will do the opposite in order to restore equilibrium, right? So that's what happens when you increase the pressure of one component in the system. Now, what will happen if you increase the total pressure of the system? Now, this is totally different because now you have to look at the different gases involved. Well, basically, the equilibrium shift is actually produced or predicted by Le Chatelier's principle. Basically, what will happen is that equilibrium will shift in the direction producing a smaller number of gas molecules in order to reduce the pressure, right? So if you increase the total pressure of the system, or if you reduce the volume of the system, which is tantamount to the same thing, then the equilibrium will shift in a direction producing a smaller number of moles of gases. So let me give an example. Let's say you have this reaction, which we saw before. Nitrogen plus hydrogen to give ammonia, right? So to balance this, we need a 3 here, right? So let's say, for example, you increase the total pressure of the system, right? So the question is, which direction will the equilibrium shift? In order to answer that question, what we do is look at the total number of moles of gases on this side compared to the number of moles of gases on this side. By the way, this should be a 2 here. Very important for you to have a balanced equation again, right? So if you look on this side, you see that you have a total of 4 moles. 3 plus 1. If you look on this side, you have a total of 2 moles, right? So basically, if you increase the total pressure, the system will try to decrease the total pressure by shifting the reaction in favor of producing fewer molecules from 4 moles to 2 moles, right? So therefore, if you increase the total pressure, this implies that the equilibrium position will shift to the right. All right? So that's how that works out. All right? Any questions about this? Any questions? Okay, so let's say, for example, I'm trying to think of a good example. Let's say you're given SO2 gas plus O2 gas to give SO3 gas. right? And let's say to balance this, we need a 2 here and a 2 here, right? So let's say in this case, I'm just going to draw a line to separate these two. Let's say in this case, you are decreasing the total pressure. All right? So my question to you is, how will the system respond? Will the equilibrium shift to the left or shift to the right? And let's hear your explanation. What do we look for in order to answer that question? What do we look for? The total number of moles on either side, right? So what's the number of moles on the left side of that equation? And what's the number of moles on the right side of that equation? Okay, so which direction will the reaction shift? To the? You're decreasing. The change that you are imposing is that you are decreasing the total pressure. So the system will respond by doing the opposite, by shifting to the left, producing more molecules of gas. You see what I'm saying? Whatever you do to the system will respond by doing the opposite. So therefore, the answer is that the equilibrium position will shift to the left. All right, and that's how that works out. Okay. Can I erase this? Can I clear this? Going once, going twice? Okay. So what I just described here earlier is basically what is stated in this line. If you decrease the external pressure, then the system will shift in the direction of producing more molecules in order to increase the external pressure. All right. Okay. Now, here's an interesting situation. What if there's no change in the number of molecules going from left to right or right to left? Here's an example. This reaction here. If you look at this reaction, if you look at this equation closely, you'll see that the total number of moles of gases on either side is the same. You have 2 moles here and 2 moles here, right? So what would happen if you change your pressure? Nothing, right? Because you have equal number of molecules on both sides of the equation, equal moles on both sides, right? So any equation where the total moles, when you add up the coefficients, total moles on either side are the same. It doesn't matter what you do in terms of the pressure. If you increase it or decrease it, nothing will happen. There will be no equilibrium shift. Neither product or reactant will be affected in terms of their concentration. All right. Okay. Okay, we have 15 minutes left. So let me move. Any questions about this? Any questions? Yes. Oh, yeah, I thought I did. Didn't I?
Yeah. You put it online.
Yeah, but then I handed it out to you. Yeah, I gave. Yeah, I gave it out in class. But it's online. You can get it in Canvas. Okay. So this is another example of how changes in pressure. Now, in this case, we're talking about the reaction between NO2. Let me write down the equation here. It's a reaction between NO2. Well, the reaction of NO2 to form N2O4. And to balance this, we need a 2 here, right? So we have 2 moles of gases on this side, 1 mole of gas on this side. So the question is, what happens when you increase the pressure from 1 atmosphere to 2 atmospheres? Again, Le Chatelier's principle comes into play. Whatever you do to the system will try to do the opposite. You're increasing the pressure of the system. The equilibrium will shift in order to decrease the pressure. And that means that in this case, it will shift in the direction favoring the formation of fewer molecules. So therefore, it will shift from 2 to 1 moles. And that's basically what is observed. So here we have 2 NO2 molecules. Just when you increase the pressure, and then when the system achieves the equilibrium, those two NO2 molecules combine to form the N2O4 molecule, all right? So that's basically how Le Chatelier's principle can explain what is observed in terms of the equilibrium shift. Okay, temperature changes. I think this is probably the last thing we're going to talk about. How does temperature affect equilibrium? Well, if you remember, I said last time that the Kc values, all the Kc values that we met, are only constant if the temperature is constant, right? What we're going to look at here in this section is how the temperature affects not only the equilibrium position, but also the value of the equilibrium constant, all right? So, in order for us to predict how the system will behave, what we have to do is see whether or not the equation or the reaction as written in the equation is either exothermic or endothermic. And I'm quite sure you all remember what those terms mean, right? If a reaction is exothermic, that means that it produces heat. If a reaction is endothermic, it means that it absorbs heat from the surroundings, all right? So, according to this, raising the temperature of an equilibrium mixture will shift the equilibrium towards the direction of the endothermic reaction. And if you lower the temperature, then it shifts the equilibrium towards the exothermic direction, all right? Now, we can explain that by considering heat as though it is a product, right? Like a chemical product, even though it's not a chemical product, but we can treat it that way for the purposes of explaining why we observe these changes, right? Now, that is true in an exothermic reaction, but we can also treat heat as a reactant if the reaction is endothermic, all right? And let me see what we have here. Okay, so before I put that up, so let's say, for example, you have a reaction that is exothermic. I'm going to use a real example, the reaction between the one that we just saw a while ago, and 2NO2 to form N2O4, right? Now, this reaction here is endothermic, right? Which means that delta H is positive. No, hold on. Is negative. So it's less than 0. It's exothermic, right? Exothermic, all right? This reaction is exothermic. So instead of writing it like this to represent that the reaction is exothermic, we can write it like this, 2NO2 to give N2O4 plus delta H, right? So in other words, this is the amount of heat that is produced when the reaction goes from left to right, okay? So let's think about it in terms of Le Chatelier's principle. Let's say you were to increase the temperature. If you increase the temperature, basically what that means is that you're removing heat, right? So you're removing heat. The system will respond by producing more heat because the system will do the opposite of what you're doing to the system. So the system will be producing heat, which means that in this case, the equilibrium will shift in that direction, right? So therefore, equilibrium position will shift to the right. And what does that mean? That means that the concentration of N2O4 will increase and the concentration of NO2 will decrease. So what does that mean about Kc? What do you think is going to happen to Kc? Let me write down the Kc expression. Kc is equal to the concentration of N2O4 divided by the concentration of NO2 squared. If the concentration of N2O4 increases, so this term here increases, and the concentration of NO2 decreases, then what happens to Kc? If the numerator increases and the denominator decreases, then what happens to Kc? The Kc would increase, exactly. So Kc will increase as a result. All right, so that's basically how temperature changes will affect the magnitude of Kc, right? What if the opposite occurs? Let me do some erasure here. What if instead of increasing the temperature, we are decreasing the temperature? Decreasing the temperature. What will happen as far as the changes will occur? Let me do some erasing here. If you're decreasing the temperature, you're removing heat, right? So let me write here. You're removing heat. So what will the system do in response to that? The system will what? Huh? Yeah, but why? I want to go through the reasoning steps. So the system will do what? In response to you removing the heat, hold on, I think I did something wrong. Okay, yeah. Oh, wait a minute. I think I made a mistake earlier. Hold on. What did I say before? When I said the temperature increases. Okay, I realized the mistake I made before. My bad, my bad. I apologize. I made a big boo-boo. Okay. Let me correct that now. ASAP. So I said that you're increasing temperature initially, right? So what happens is that you're increasing this, which means that the system will remove the heat, and that means that the system equilibrium position will shift to the left. So let me correct, oops. Let me correct that down here. So here, the system will shift to the left. All right, so let me correct the error here as well. So please make that correction along with me. So the equilibrium will shift to the left in order to use up the heat that is added. So that's going to change these errors as well. Oops. So that means that the concentration of N2O4 will decrease. The concentration of N2O4 will decrease, and the concentration of NO2 will increase, which means that Kc will decrease as a result. All right, I apologize for that. So that's what happens if you increase the temperature. All right. If you decrease the temperature now, the reverse will happen. So let me just erase all this here. So if you decrease the temperature, that means you're removing heat, which means that the equilibrium will shift to the right. Which means that the concentration, so instead of shifting to the left, it's going to shift to the right, which means that the concentration of N2O4 will increase. So the concentration of N2O4 will increase, and the concentration of NO2 will decrease, which means that the Kc value will overall increase. All right, so that's basically how we do this. Now, this is very important, especially when it comes to making compounds industrially, right? typically chemical engineers would be involved in this process. And they would have to consider all the different factors for a particular reaction in order to favor a particular product. In fact, the reaction that we mentioned before, N2 plus H2 to give NH3, that reaction is basically, named after a guy by the name of Fritz Haber, right? He was a German chemist, and he lent his considerable chemistry skills to the war effort during World War I. And, he's generally known as the father of chemical warfare, right? So he basically was involved in producing a lot of chemical weapons back then. But another one of his contributions to the war effort was this reaction right here, right? He basically came up with a method of making ammonia, which can be used to make explosives. And this became necessary because the raw materials that was needed to make explosives had to be imported from South America. But when the Allies cut off those shipping routes, then Haber get to work, and he, formulated a method of making this compound, right? And he had to take Le Chatelier's principle into account and apply it when doing this. He basically used conditions of high pressure for the nitrogen and hydrogen, high pressure overall, and low temperature, because this reaction here is exothermic, right? Delta H negative for this reaction right here. So and of course he had to use a catalyst. He came up with a special catalyst, combination of metals, that resulted in his being able to make ammonia in very large quantities. Unfortunately for him, Hitler took over. He was a Jew, by the way. So unfortunately for him, Hitler took over, and he had to basically leave Germany in a hurry as a result. So Hitler didn't care about his contributions to World War I. As far as Hitler was concerned, he was worthy of death simply because he was Jewish. So that's how that worked out for him. Okay, that's it for today, folks. So based on what we have covered, let me discard this. You should be able to do, where is the assignment? Where is the assignment? Okay, so number 6. You should be able to do number 6. Oh, let me quickly mention catalyst. I thought I was finished. Nothing much to say about that. Simply put, if you add a catalyst to the equilibrium mixture, it will not affect the rate of the reaction, right? Or it will not affect the equilibrium position. Let me just say that. Why? Because the catalyst will speed up both the rate of the forward and reverse reaction to the same extent. So therefore, the net result is no change in equilibrium. Basically, equilibrium will be achieved faster if you start off with, let's say, the reactants initially, but the equilibrium position will not change. The Kc value will not change. Basically, there'll be no net change in terms of the equilibrium position when you add a catalyst. And that's all I have to say about that. Now we're finished. All right. So going back to the assignment, in terms of the questions that you can do, let me see here. Okay, you won't be able to do number 7, but you should be able to do number 8. So, oh, no, you won't be able to do number 8. You only be able to do part of number 8. Okay, so I don't think you are able to do anything else. So the only question I would ask you to look at right now is question number 6. One last thing. So I've decided to postpone the test from Wednesday to next week, Monday. And the reason for that is that not all of you have submitted the additional questions that were added to assignment number 2, right? Please do so by today, all right? Because what I want to do is add up all the points for your assignment, the initial assignment plus the additional questions, and I want to send it back to you, and I want to post the answer key as well. So make sure that you do that by today so that I can get all that done, and you'll have your assignment and the answer key to help you to review in preparation for your test next week. Yes, sir.
Do you have any more physical copies of assignment 3?
I may have it in my office, but I can't go there right now because I have a lab class.
Okay, well, yeah.
Oh, right, so, yeah. If I had more time, I could just print a copy, but like I said, it's in Canvas, so. Okay, somebody has a question. Do we have a study guide? That's what Miss Jones is asking. And the way I look at it, the study guide would be your assignment and assignment keys. All right? If you follow those and understand what's happening there, you should be in good shape for your test. I would also recommend that you try as many questions from your textbook as possible. All right? I hope that answers your question, Miss Jones. Okay, folks, so that's it for today. See you guys on Wednesday. You mean the test? Yeah, mostly, I mean, you might be asked a couple of questions like definitions and so on, but.
Okay.
But it's mostly problem solving.
You allowed any notes on the test?
No notes. The only thing you'll be allowed is your calculator. I'll provide the tables and you'll get a sheet of scratch paper and that's it.
You get like a formula sheet. I mean, there's already many formula.
Right. Well, actually, the tables I provide some formulas. Yeah,
So we'll just have everything.
yeah.
All right. I don't know what it was with rate law.
What's that?
I don't know what it was with rate law questions.